recording, because what that means is that if you ever are away, you'll be able to watch the lesson video. In fact, let's go over here and look. On our team, there is a channel called Lesson Videos. So after school today, I'm going to take this video and I'm going to post it on YouTube up to there. I do not edit them. They're just like live. So if there's a section where in the middle of the class you're working for 20 minutes, there's going to just be a 20-minute gap in the middle and you'll have to fast forward through it. But it does mean that if you're away, you will be able to see the lesson, or if there was something you didn't understand and you just want to go back and review it, you can do that too. Okay? So that's one of the things that is on our team that's quite useful. Another thing is we have upcoming quizzes and tests, of which there are none right now because it's only day one. Yay! The other one is homework. I haven't put anything up there yet because I just haven't had a chance, but it's going to look like pages 13 to 14 in Unit 0, and in the yellow book, pages 1 to 3, because there's going to be some video, some reading, and some Hebden exercises. Okay? I'm going to breathe. Okay, here we go. All right. We have a course outline, so if you ever need to see the course outline, you can click on that. It's there. I'm not going to look at that one. I'm going to look at this one. This is in our class notebook. And we're going to go through this super quickly, okay? Because this is an academic grade 12 elective. So we're not going to spend very much time being like, hello, how are you? What's your name? I'm going to learn your name as we go, okay? The one thing I do need to point out is that these workbooks, we need to pay the printing cost of them. So there is a charge of $40, okay? It's not just for the one book. If you're looking at it going, that's a pretty expensive workbook, you're going to get 6 workbooks, okay, along with the answer keys. All right, and so that's $40. It can be paid by school, cash, online. You can also pay by cash or check at the office. And if you could please pay by this Friday, that would be wonderful. Now, if this cost represents a hardship to your family, please speak to your counselor and the fee can be waived, okay? If you are an international student, you do not need to pay, as the workbooks are already included in your international fees. I'm not going to go through what you need to do for student success because you are in grade 12 and you've chosen to sign up for a difficult grade 12 course. Work with intent, communicate with me, take charge of your own learning, use some proven study techniques, do your best, forget the rest. Okay, moving right along. You can expect to have at least 30 minutes to an hour of homework each evening, okay? And a minimum of 2 hours on the weekend. Don't forget to check Teams regularly. You all know about Flex Time and the Peak program. We have 6 units. The first one, well, we have Unit 0. We're going to do a little review of solutions because how many of you remember what happens when we put an ionic solution, an ionic compound into water? Anybody? That's what I thought. That's why we're reviewing that right off the bat, okay? But other than our sort of little beginning unit, we have reaction kinetics, equilibrium, solubility equilibrium, acids and bases, which also includes equilibrium. So are you getting the idea that equilibrium is going to be very important in this course? Because part 5, acids and bases, that's also equilibrium, and then electrochemistry, which is not equilibrium. You will have 10% of your grade on quizzes, 15% of your grade on labs, and finally, 75% of your grade will be tests. Now, if you had me last year in grade 11 is a very skills-based course, and I can come up with 1,074 different problems about how to convert moles to grams and grams to moles, okay? Because that's a skill, and I can just put in different numbers, different compounds, whatever. Grade 12 is much more conceptual. So I cannot come up with 1,000 ways to ask you, do you understand this concept? So last year in Chemistry 11, if you had me, we had re-quizzes. There are no re-quizzes this year. Okay, but they're only worth 10%. So if you bomb one, it's actually not that bad. Okay, it's like, okay. All right. Tests. No retests. Whoops. Okay. Because you're grade 12, you're almost in university. There's no re-quizzes, there's no retests. Unless there's a really good reason, you must be here on the day of the test. If it turns out that you are habitually away for quizzes and tests, I have harder versions of everything and I will bring them out. Okay. Now, don't come in if you're sick on the day of a test, but you know, there's some people who are here every day. There's always one or two. And then every time it's a quiz day, oh, they're away. Oh. And then there's the next quiz, and oh my God, they're away again. Oh. Uh-huh. And then they're away again, and oh, then I have a reason, and oh, I have this, and oh, I have that. It becomes a pattern, and when it becomes a pattern, I'm not going to put up with that. I'm just going to give you a harder version of the test and be done with it, okay? So you don't want to do that because the harder versions are like nasty, okay? Pencil, you need to bring a pencil. Eraser, you need to bring an eraser. There's a whole bunch of other things here too, but you will also want to have a binder. Why do you need a binder when we have all these workbooks? Well, because there are things like these wonderful little, these wonderful little doodads, and you want something to put them in so they don't get lost, okay? Plus, although most of our work is done in the workbook, we'll also be taking free-form notes sometimes, so you will want to have some blank paper. Now, what if you don't have blank paper? Well, fortunately, at the back of the classroom, guess what we have here? What does it say? Oh my God, you just got free blank paper. Okay, that's what it says, free blank paper. So you can help yourself to that. Basically what it is photocopies I've made where it was wrong or I had too many copies and you're just gonna write on the back, okay? But it is there. And you will need a scientific calculator, okay? You will not be permitted to use your phone on tests or quizzes. I think that's pretty obvious. Yes, is good? All right. Is there anything else on here? No. So we'll go back to Teams. Have I missed anything else? There is going to be a section called class notes. I haven't uploaded it yet, but it is going to be when we go to our class notes and let's say I wanted to see this with all the writing on it. That's where you'll be able to see this document with all the writing on it. Okay, I'll point it out again once I have it uploaded. I'll show it to you again next day. All right, I think that is it. Oh no, general. The general channel is important because in the general channel, up at the top, you will find files. So unit 0, Chem 11 review, you can click on that. Like let's say you went home and you forgot your workbook. Well, let's see. Oh, solutions review. The whole booklet is here. The whole key is here. And if you want individual worksheets from the book, they're all here individually as well. Okay. We can also go to kinetics. And you can see the workbook is here, the worksheets are here, and every time I put in a new unit, I'm also going to be putting in the reviews for them. So if you ever want to get started on the review early and I haven't handed it out yet, you can do that. But I will also be giving you hard copies of everything. Okay? Is good? Okay. What's next? Not Teams. So let us then, we're going to start, can we start content? Yes, good. All right. We are going to go to the little Unit 0 Solutions Workbook, and we're going to go to page 1.
What happens when stuff dissolves?
Okay. Now, have I sped him up? I'm going to put him on 1.25. Let me know if it's too fast. He does tend to talk slowly. Yes. Yes.
Is there going to be a final exam?
That's all going to depend on how far we get right now.
Okay.
Yeah. I'll let you know, like, May-ish.
Also,
Yeah.
I don't know if it's possible as a budget too long, but it's any better than it has to be.
No. I know, it's not nice, but quizzes are only worth 10%. And what you'll find is if you bomb one quiz, it won't actually make that huge of a difference on your grade. Oh, and the other thing is, too, that I forgot to mention, is that I've been doing this chemistry 12 gig for a long time, like 28 years, okay? And so I taught it back when we had provincial exams. So I would get to see the grades that I gave my students before they went into the provincial exam. I would get to see what their school average was, but then I would also get to see what their exam mark was, okay? And as it turns out, the school mark that I gave them and the exam mark for my class usually were like this. They were the same, okay? But we also got to see statistics for the entire province. So what I saw for the entire province is this was their school mark going in, and this was their exam, this was their school mark going on, and this was their exam mark. 3% lower, okay? What that tells me is that I mark 3% harder than, I feel like my hands are going the wrong direction. This is the second time I've done this today. But at any rate, it meant that I worked 3% harder on average than the province. So what I do is when you get to the end of term, I simply add 3% to your grade. So if your grade says 85, that will become an 88. If your grade says 52, that will become a 55. If your grade says 99, well, we can't go over 100, so it'll be 100, okay? All right, so that also helps take care of if you bomb a quiz, you know you're getting that 3% back, so, all right? All right, let's hang out with Tyler for a little bit and find out what happens when stuff dissolves.
I mean, like, what happens to the atoms and molecules that make it up? I want to talk about two things here that you dissolve all the time: salt and sugar. These two things look very similar. They're both like kind of white powders made up of little grains, and you could pour both of them into water and stir around, and you see the grains get smaller and smaller, and maybe break apart, until eventually they've totally disappeared. They've
Is this too fast? It's okay?
completely dissolved in the water. That's what you see with the naked eye. But if you had atomic vision, and you could see the atoms that make up salt and sugar, what would it look like as these grains broke apart and became invisible? That's what we're going to talk about here. So it actually depends whether something is an ionic or a covalent compound.
Ionic or covalent compound. Tell your partner or your neighbors or anyone close to you what you remember about ionic and covalent compounds.
Covalent is just salt is an ion.
Okay, let's see if you remembered correctly. Let's see what Tyler tells us.
It depends on what it would look like when it dissolves. So over here we have salt, and this is an ionic compound. This is what a grain of salt would look like, and it's made of sodium ions, Na+, which are metals, and Cl, chloride ions, these blue things here, which are nonmetals.
Okay, so ionic compounds are made of metals and nonmetals. And if you look up at that periodic table over there, what color are the metals? The metals are blue, and the nonmetals are pink. Okay?
So salt is an ionic compound made of metals and nonmetals. Sugar, on the other hand, is a covalent compound because it's made of nonmetals, carbon, oxygen, and hydrogen. And these nonmetal atoms are connected together into a molecule.
Okay, so we have a molecule here. This covalent compound makes a molecule. Is this structure of the salt over here, is that a molecule? The salt really is a three-dimensional structure. He's only drawn it in 2 dimensions because it's really hard to draw these 3-dimensional structures. But basically what we have is we have an alternating sodium chloride, sodium chloride, sodium chloride, sodium chloride, sodium chloride in 3 dimensions. Does anybody remember what this structure is called? That is a crystal lattice, okay? It's an ionic crystal lattice. Is it going to be the end of the earth if you don't know the term ionic crystal lattice in grade 12? No, probably not. It's more of a grade 11 concept, but it's still useful. And when we have our metal, does anyone remember what the charge is of the metal? Yeah, we have positive and negative. Which one is positive and which one is negative? The metal is the positive, and the nonmetal is going to be the negative. And do you remember the name that we have for positive ions? Positive ions are called cations because cats have paws. So cations are positive. Okay? And these are going to be our metal ions. They're positive, those are called our cations. And the opposite of a cation is an anion, and those are our negative ions. And what are those made of? Nonmetals.
So a grain of sugar would look like this. It would be a bunch of these sugar molecules all kind of lumped together. Notice that a grain of sugar is a lot more messy. It's not nearly as well organized as an ionic compound, this grain of salt over here. Anyway, let's look at what would happen when we dissolve these. We'll take a grain of salt, dip it in the water, and start stirring around. With our atomic vision, we're going to see that the atoms that make up this salt are going to come apart from each other. They're going to break apart, and they're all going to start floating around in the water individually. This is what it looks like when salt dissolves. Okay? Now let's take our sugar. Here's our grain of sugar. It goes in the water, we stir it around, and the grain of sugar is going to break up like we saw the grain of salt break up, but it's going to break up in a different way. It's going to break up into the individual molecules that made it up. But these molecules are not going to break up into the individual atoms. They're going to stay as molecules, and those molecules are going to start floating around in the water. A big mistake that people make, I don't want you to make this mistake, is they think that when sugar or other covalent compounds dissolve, they think that the atoms that make up the molecules totally break apart. And then you end up with a glass of water that has all these carbon and oxygen and hydrogen atoms just floating around. That does not happen. Big red X. Instead, the molecules stay together. Well, the atoms in the molecules stay together. So this is a big difference between how covalent compounds dissolve, where the molecules stay molecules, and how ionic compounds dissolve, where the grains of these things like salt actually break apart into the individual atoms.
Okay, and we're going to take just one moment to look on our actual document here, because this process where the ions break apart has a name. Does anyone remember what it's called when the ions dissolve and they break apart? We're on page 1 of our, so you'll want to open it there. Yeah, good stuff. Okay. Anyone remember what that process is called? The ions dissociate. Okay. And if you've forgotten, oh, guess what? It's right there. The process is dissociation. You've probably heard the word association. Yeah? Have you guys heard the word association? Okay, an association is when a bunch of people get together to do something. So association is coming together. Dissociation is breaking apart. Okay? So our ionic compound dissociates into individual ions. Now, what happens with the sugar is that the clump of sugar molecules doesn't break apart into atoms. Each individual sugar molecule stays intact, okay? But the sugar molecules then float separately from one another, and that is called dispersion. So basically, the sugar molecules are dispersing, okay? And we could write the dissociation equation, say for calcium chloride. We have calcium, Ca, chloride, Cl2, and that is a solid before we put it into the water. When it dissociates, we get the calcium ion coming out. What do you notice about the ion? What does it have to have? It has to have a charge on it. Otherwise, it's not an ion, okay? And once it is dissolved, do you guys remember what this little AQ stands for? Aqueous. And what does aqueous mean? Dissolved in water. Don't worry, we're going to write this down a little bit later, okay? Now, do you notice that little 2 there, that little subscript 2? That tells us how many chlorines are there. 2. In fact, there are not 2 chlorines, there are 2 chlorides. Chlorine would be neutral, chloride would be the ion that has the negative charge. Okay? Yes. But because we have 2 of them, we need to write that 2 there. Okay? And it's also dissolved in water. Now, this is how we would write the dispersion of sugar. This is a sucrose molecule. It's solid. There are 12 carbons, 22 hydrogens, and 11 oxygens in a sugar molecule. And when we're finished dissolving it, there are still 12 carbons, 22 hydrogens, and 11 oxygens in that sugar molecule. Okay, they have not split apart. So we just show the change of state. It has gone from being solid to being dissolved or aqueous. Okay? All right. Back to Tyler. I think that might be it.
So, to answer the question, what does it look like when something dissolves in water? The short answer is, it actually really depends whether you're talking about an ionic compound or a covalent compound. If it's an ionic compound, it's going to break apart into all of the individual atoms. But if it's a covalent compound, the clump of the molecules will break apart into individual molecules once it dissolves, but the molecules themselves will not break apart into atoms. They will stay as molecules dissolved in the water.
Okay, and that's it for that. Now, we are also going to carry on and watch a little bit, not the whole thing,
Once
but
a sugar molecule is surrounded by
some of the next one. I think it's on page 6. Let's just check. Well, maybe not page 6. No, it's on page 2. Page 2. Okay.
In this video, we're going to talk about how things dissolve in water to make aqueous solutions. We're going to look at an atomic view of how water molecules dissolve solute particles, which is a process known as solvation. And we'll see that solvation occurs differently for covalent and ionic solutes.
So we're really looking at the same process he just showed us. We're just looking in a bit more detail here, okay?
Let's start by making an aqueous solution, one that you've probably made yourself many times. We'll dissolve a sugar cube in water.
Do you guys know the words solute and solvent? Describe to your partner what is the difference between the solute and the solvent. Okay, so which one gets dissolved? The solute or the solvent? Solute. And that would make water the solvent. Yeah.
To dissolve. It's not instantaneous. Let's take a closer look at what's happening during this dissolving process. Here's our sugar cube, and let's imagine that we could zoom into it many times and see the atoms and molecules. We'd see that the sugar cube is made of trillions and trillions of molecules that look like this. Table sugar is actually a compound called sucrose. Here's its chemical formula, and it's made of carbon, hydrogen, and oxygen atoms. Because these elements are all nonmetals, you know that sugar is covalent. Its atoms are connected by covalent bonds made by sharing electrons.
What makes a bond covalent? What happens with the electrons? They're shared. What happens in an ionic bond with the electrons? There's a transfer of electrons. Who gives the electrons away in an ionic bond? The metal gives away the electrons, and who takes them? The nonmetal. That's why the metal becomes positive, because it loses some negatives. And that's why the nonmetal becomes negative, because it gains some electrons, which are negative.
And there are different ways that we could show the molecule. So here, we're representing the sugar molecules with a 2D Lewis structure that shows the covalent bonds. If you made this into a ball and stick model, it would look like this. But a more accurate depiction of sugar is actually closer to this. We call it the 3D model. It's a bit blobby and kind of hard to see all the different atoms. But we're going to use this model for now because it will better illustrate what we're talking about here, which is how molecules interact. Now, let's look at water, which is our solvent. Water has a chemical formula of H2O, and here's some 3D models of water molecules.
Now, just before we carry on, I'm going to remind you a little bit about water. Of course, it's got the oxygen and the 2 hydrogens. And this little symbol here, I'll draw it bigger over here. This symbol kind of looks like a D. Okay, it's the Greek letter delta. It's a lowercase delta. Okay, and that lowercase delta means slightly. Okay, so if we look over here, this end, the oxygen end, has been labeled slightly negative. Yeah? And the hydrogen end has been labeled slightly positive. And that's because oxygen, and I don't know, I think if you were in my class, we might not have gotten into electronegativity, so you might not have any idea what I'm talking about, but oxygen is more electronegative than hydrogen, so it tends to pull electrons towards itself. So you end up with a partial negative charge here and a partial positive charge there. So we have a negative end, the oxygen end, and we have a positive end, the hydrogen end. But we could call these ends, instead of calling them ends, we could call them poles, like the North Pole and the South Pole. But in this case, it's the positive pole and the negative pole, which means that this molecule is a polar molecule. Okay? Are you going to have to explain any of this for grade 12? No. okay? But it's a review of what happened in grade 11 so you can remember how it works. So we're going to take a look, bearing in mind that water is a polar molecule. We will use that information in the context of dissolving sugar.
Now, we want to look at dissolving here. So let's zoom in on our sugar cube in the water. We're going to look at this edge right here. So here's the edge, zoomed in millions and millions of times. The sugar molecules are all clumped together. This looks pretty confusing, so we're going to clean it up a little. We'll reduce the number of sugar molecules and we'll arrange them in neat little columns. See? This is easier to look at. But just remember, things are more messy in real life. Also, remember that this sugar cube is sitting in water. So now let's add the water molecules that are on the edge of the cube over here. There we go. We've got the water and the edge of the sugar cube. Now, for the water to dissolve the sugar, water molecules have to bump into the sugar molecules. They got to bang into them, sort of like this. And they can only do...
So, in order for the water to dissolve the sugar, what does it have to do? The water has to bump into the sugar. Okay, so it has to bump into the sugar.
do this at the surface of the sugar, so it takes some time. Then, after bumping into the sugar, the water molecules kind of work their way in between the sugar molecules and surround them. You can see that happening here. Once a sugar molecule is surrounded by water molecules, they carry it into solution. Here, you can see that one of the molecules of sugar is surrounded by water molecules and it's carried away.
Now, just before we carry on, if you want to fill in those boxes on page 4, water molecules collide into the solute, and then the water surrounds the solute. So this is on page 4. The water molecules collide into the solute. And that word collide is going to become important in our first real chemistry 12 unit, because it's not only how particles dissolve, but it's also how they react. Let's just get rid of the caption for a second here. There we go. And the water carries the solute into the solution. Don't worry if you don't get all the boxes filled in here. Like I said, you're not going to be tested on this, okay? But what you can notice is that, let's take a look at this little water molecule right here, okay? Which end is pointing towards the sugar? The positive hydrogen end is pointing towards the sugar. And guess what I see on the sugar right here? I see a red oxygen, and oxygens tend to be negative. What does positive do to negative? They attract. So what's going to happen is that this water, the reason that these water molecules are able to pull the sugar crystal away from the sugar molecule away from the entire crystal is that they pull, the positive ends pull on the negative part of the sugar, and the negative end, you can see that's quite close to a hydrogen, which tends to be positive. The negatives will pull on the positive part of the sugar, and they will be able to pull it away from the other sugar molecules.
Keep your eye on this one here at the top, and there we go. It got surrounded and carried away. As the water molecules carry the sugar molecules into solution, new water molecules can reach the undissolved sugar over here, and the process continues. I think this one's next, and there we go. Another one gets surrounded and starts to float away. And this is what's happening at the atomic level as sugar dissolves. All these sugar molecules are coming apart from each other, and they're getting surrounded by water molecules, and they're floating off into the solution. Now notice one thing here about how the sugar molecules float away. This is super important. The sugar molecules separate from each other, okay? But
What don't they do? Sugar molecules separate from one another, but they do not dissociate. They do not break apart.
The whole molecule stays together. The molecules don't break apart into their atoms. In other words, the dissolving process doesn't break the covalent bonds inside a sugar molecule. The
Okay, so his hands in the
atoms in the molecule stay together as the sugar dissolves.
Okay, so I think we're actually going to skip some of the rest of this. So we're going to skip page 5 and we're going to turn to page 6. Okay, don't worry if you don't get everything on page 5. You can go watch it if you want to, but you don't have to. Like I said, not being tested. We're going to now go to the cube dissolves hydration shell. So here's our little hydration shell. Okay.
Are called hydration shells.
You
might
don't need
also
to know
hear
that
them
word.
referred to as solvent cages.
You don't need to
They
know
make this
that
little
word either.
cage or shell around the solute. Just keep in mind that they surround the entire solvated particle. So they're actually in 3D, right? Even though we're just drawing them in 2D here. So that's hydration shells or solvent cages. Now, let's switch gears here and see how ionic compounds dissolve.
What's this structure here called? That is our crystal lattice. And what is it made of? Is it made of atoms? It's made of ions. Atoms are generally neutral, okay? If we say atom, we're usually referring to a neutral particle. If we say ion, we are referring to a positive particle or a negative particle.
Sugar, which we looked at earlier, that's a covalent compound. But the process of solvation works differently for ionic compounds like sodium chloride or table salt. We know that sodium chloride is an ionic compound because it's made of a metal, sodium, and a nonmetal, chloride. Here's a grain of salt. If you could zoom down to the atomic level, you'd see that a salt crystal is made of trillions of tiny ions all packed together. Sodium ions have a positive charge and chloride ions have a negative charge.
And when two things attract, we call that what kind of attraction? Electrostatic. That's when positive attracts negative. That is called electrostatic attraction. And that's on page 7. Electrostatic attraction. Again, you're probably not going to need to use that word in Chemistry 12.
These ions are bonded together by electrostatic attraction. It's kind of like trillions of tiny magnets all stuck together. So let's see how solvation happens with an ionic compound. We'll zoom in to get an even closer look. When you put sodium chloride in water, the water starts bumping into the ions at the surface of the crystal. And then the water molecules surround the ions and pull them apart and carry them into the solution.
So very much like the sugar, but in the sugar, we don't get individual atoms. In the ionic compound, though, we do get individual ions. So I'll give you a minute to fill in those boxes there at the bottom of page 7, and then we're going to look at the particles more closely. Okay, so let's just take a look here. Here we have, what kind of ion is this green one? What's in the middle of that green thing? What does it say? Negative. So what kind of ion is it? It's an anion. Okay, so we have an anion here. It's negative. What do you notice about all the water molecules surrounding that anion? All of them, which end is closer? The hydrogen, the positive end. Okay, does that make sense? Right? Okay, so these positive ends of the water will surround the negative ion and pull it away. Here's our positive ion. What do we call positive ions? Cations. And what end of the water is surrounding those cations? The oxygen, which is the negative end. Okay? We're going to leave that there. There's more stuff. Like I said, if you're interested, you can read it, but we're not going to. So we're moving on to page 11. 1-1, page 1-1. So we are going to focus on the dissociation process here. If we're focusing on dissociation, what kind of compounds are we looking at? Ionic, okay? So this is when ionic substances will dissociate or separate in the water. And what we're going to be doing on this worksheet is we're going to write the dissociation equation for the salt. Okay, so we're going to write the dissociation equation for the salt. Then we're going to identify the ratio of the particles. And then for a few of them, not all of them, just because I'm never going to make you draw this, okay? But it does help you visualize it. So for the first 4 of them, you're going to draw the ions present in the correct ratio, okay? So how is this going to work? Well, let's take a look at this example here. We have sodium ions, and we have these NO3 ions. If you need to use your pink booklet, please feel free. The polyatomic ion chart is on page 3. So if you open it up, you'll find the polyatomic ion chart there. Can you name that compound, NaNO3? Tell your partner if you can, when you think you can name that compound. I'm hearing a lot of good answers out there. So Na is sodium. And NO3 is nitrate. Except I've done something a little bit wrong here. What have I done that is wrong? What am I missing? I'm missing that negative charge on the nitrate, and I'm missing the positive charge on the sodium. You will lose marks in Chem 12 if you don't show ion charges when the ions are separated from each other, okay? So you'll notice when the compound is written together, we don't write the charges, but when we separate them, we do write the charges. Yes. Now, if we look at the compound NaNO3, what is the ratio of sodiums to nitrates? So here's a sodium nitrate. What is the ratio of sodiums to nitrates? 1 to 1, okay? Don't get fooled by that little 3 down there. That 3 doesn't mean there's 3 nitrates. What it means is that you have a nitrogen atom attached to 1, 2, 3 oxygen atoms, and you only have 1 of those, okay? So don't get fooled by that 3. It just means that you have 1 nitrate, 1 N with 3 O's on it. So we would write our dissociation equation. Don't forget, we'll show that we start with a solid, and then it dissociates into Na, and we must remember to write the plus, and we must remember to write the AQ. So we need to have the charge. And what does AQ stand for again? Aqueous. And what does aqueous mean? Dissolved in water. So we've shown our ions separating. We have a plus in between them to show that they are separate from one another. And then we have the NO3, and again, we have the charge, and we have the aqueous. Is aqueous the same thing as a liquid? How do I make something into a liquid? Like, let's say I had some iron. Okay, I have an iron bar. And it's a solid. How do I turn that into a liquid? I absolutely melt it, yes? I melt it, I apply heat. Yep. And I started with pure iron and I finished with pure iron. Yeah? But when I take sodium nitrate, I don't finish with, and I dissolve it in water, I don't have pure sodium nitrate anymore. I have a mixture of sodium nitrate and water, okay? So that's the difference between aqueous and liquid. Aqueous means it's a mixture, it is a solution with water, and liquid means you have melted it using heat, and you still have that pure substance. So if I were to draw this, every time I draw a sodium ion, I would also need to draw a nitrate ion because they're 1 to 1. So in my beaker, I have 1, 2, 3, 4 Na pluses, and I have 1, 2, 3, 4 NO3 minuses because that is a 1 to 1 ratio. So that was a fairly nice, straightforward one. So let's take a look at our next example. We have K2S. And let me know if I ever move too quickly or too slowly. I'm happy to adjust my speed. What is the ratio of K to S? It's a 2 to 1 ratio. Within this crystal, I have 1, 2, 3, 4, 5, 6 K pluses, and I have 1, 2, 3 S 2 minuses. So I have a 2-to-1 ratio. So every time we dissociate a K2S, we get 2 Ks and 1 S. Which is why when we write the dissociation equation, yes, sorry.
It's like you kind of a stupid question.
No,
But why can I also write this as a 1-to-2 ratio?
you can write it as a 1-to-2 ratio, it doesn't matter. I'm just writing it as 2-to-1 because the metal comes first in the compound, but yeah, it doesn't really matter.
So theoretically, I can also write it as 1-to-2.
Yeah, and in fact, you could, it's a little bit odd to show it this way because we usually try and keep everything like looking like it, but it would also, it would not be incorrect to write the equation like this. We would have our K2S solid. You could write the S2 minus first, and you could write your 2K plus second, because the order of the products doesn't matter because they're floating around separately from one another, okay? But it is much more usual for us to keep them in the same order they were in the compound. It just makes life a little easier for our poor little brains at the end of the day, right? So, yeah. All right, so don't forget, if you have a little 2 there, then you need to draw a coefficient in front of the ion. Is good? All right. Okay. Now, common errors. We've talked about most of these already. You must write the ion's charge. If you don't, you will lose a half a mark. And you must, if we're writing a dissociation, write the aqueous because the states in this case are important. We are going to come to some instances where we don't need to write states, but I'll let you know when those come about, okay? Now, if we have MgCl2, it dissociates, and we get 1 Mg. Now, what's our other product? Is our other product Cl2, aqueous, or is it 2Cl minus aqueous? Tell your partner what you think. Now, I'll let you know, a lot of people will think that it is the Cl2 because they'll remember correctly that when you have chlorine, it's a diatomic element. But we have a problem. Chlorine, do you remember what your diatomic elements are?
Yeah,
Okay, so we have Dr. Brinkelhoff, or have no fear of ice cold beer, or if you start on element number 7 and you draw a 7, that's your hockey stick, and then the puck is hydrogen. Those are the ones that are diatomic, made of 2 atoms. Now, why is chlorine, when it is in its elemental state, do you guys know what I mean when I say elemental state? That means when they are pure elements, not part of a compound. So chlorine. Chlorine is in group 17. So how many valence electrons does it have? All elements in group 17 have 7 valence electrons. Okay, and we can count them up. We got 1, 2, 3, 4, 5, 6, 7. That's our Lewis dot structure for chlorine. In order to become stable, how many electrons should chlorine have? It should have 8, okay? And so what it's going to do is it's going to get together with its little buddy here. They each have 7, but they are now going to do what? They're going to share those 2 electrons, and we form a covalent bond, okay? And now this chlorine has 1, 2, 3, 4, 5, 6, 7, 8. And this guy over here has 1, 2, 3, 4, 5, 6, 7, 8. Everybody has a full valence shell. Now, what I'd like to know is, what is the charge of elemental chlorine? What is the charge of elemental chlorine? Is it positive, is it negative, or is it neutral? It is neutral. Yeah? Because each chlorine atom has 17 protons and 17 electrons. And if you have 17 positives and 17 negatives, what do you get? 0. And this guy over here also has 17 protons and 17 electrons, which together give me 0. So when I put those 2 together, then I have 34 protons and 34 electrons, which means that my overall charge is still 0. So that means that elemental chlorine is neutral. So if we were to write the symbol for this, we would write Cl2, and we could, if we wanted to, put a little 0 up the top. It's not usual to do that. Usually we just leave it blank. Yeah, but it is neutral. All elements, when they are on their own, are neutral. Okay? Now we can contrast this with magnesium chloride. Now chlorine is no longer on its own. It is together with another element. It's together with magnesium. And magnesium is in group 2. So it has 2 valence electrons. And you'll notice that chlorine has a little gap here, And my other chlorine has a little gap right there. And so the electrons from magnesium can move over and slot in right there and right there. And the magnesium has now lost 2 electrons. If something loses 2 electrons, what charge does it become? Positive, and it becomes 2 positive. So that's why we have the 2 positive for the magnesium. And each chlorine has gained 1 electron. Okay, and if it has gained 1 electron, the charge is negative. Okay, so with each of them have a negative. So when chlorine is in a compound, it's no longer neutral, it is negative. It has a charge. Well, at least if it's in an ionic compound, we won't worry about the covalent ones right now. Okay? So when we show the dissociation, this is a compound. Even though these two are written separately, they are still a compound. There is no way that I could take the chloride out by themselves. Okay? I might be able to pair chloride up with somebody else and remove it, but then it would still be part of a compound. Maybe I could pair the chloride up with, calcium or something like that. But it would still have a partner. It would still be a part of a compound. Okay? And that's why we have the 2 there and why it's not diatomic. Okay, your homework is pages 13 to 14 in Unit 0. And in the yellow book, there's going to be a video for you to watch, maybe a couple little videos. They're quite short. If you find that watching the videos, you're like, oh, hey, hang on, didn't we just do this in class and I already know it? Then you can skip it. Okay? There's some reading. And there are some exercises in Hebden for you to do as well. So pages 1 through 3 and 13 and 14 in Unit 0. Yes, you can absolutely take a picture of that. And I will also be putting it up on Teams momentarily.